Hi everyone, we're going to be taking some notes over heat transfer today, and this goes along with what you saw in class with the demo, looking at things of different temperature being put into contact with each other. So let's start out by defining heat. Heat is defined as the thermal energy that flows from a warmer object to a cooler object. We're going to represent heat by the letter Q, lowercase q. Heat is measured in either calories or joules. Calories, C-A-L, joules, capital J. We use joules in chemistry more than we do calories, so we're going to be using that for our units. And if we look at kind of what joules are, it takes 4.184 joules to raise the temperature of 1 gram of pure water 1 degree Celsius. So it kind of gives you an idea of how much energy a joule or 4 joules really is. And then sometimes you'll see the units kilojoules, K, capital J, and there are 1,000 joules in a kilojoule, just like any other metric measurement with kilo as the prefix. So those are our units. That's the variable that we're going to use to represent heat that's being transferred between objects. Now, when you talk about heat transfer, you have to define a couple of things. You have to define the thing you wish to study as the system. So if we're looking at, an ice cube melting, that would be the system. If we're looking at a chemical reaction, that would be the system. We're specifically looking at what's happening as the system. Everything else is going to be considered the surroundings. So the table, the air, maybe your hand or the beaker that something is happening in, that would be considered the surroundings. So in this picture, if the ice cube is the system, then your hand would be the surroundings. And we know that your hand is at a higher temperature than the ice cube, so heat would be transferred from the warmer thing to the cooler thing. In this case, from the surroundings to the system, which is the ice cube. Over here, we can define the fire or the burning of the wood as the system. And that system is releasing heat to the surroundings, which would be the air and your hands and anything else around it. So when we're looking at heat transfer, we have to make sure we know what is the system, what is the surroundings, so that we can look at the direction of the heat transfer. Is it going into the system? Is it coming out of the system? Now we can define these processes as exothermic or endothermic. In an exothermic process, heat flows from the system into the surroundings. So the temperature of the surroundings goes up. You can see a good example of that here. Whatever is going on inside this beaker is releasing heat to the surroundings. If we consider ourselves part of the surroundings, if you touched this beaker, you would feel it as hot because you're feeling the heat being given off. In an endothermic process, heat flows from the surroundings into the system. So the temperature of the surroundings goes down. If we are the surroundings and we touch this beaker, we would feel cold because heat is going from our hands into the system. So we would feel that loss of heat, which actually means we feel cold. So endothermic, heat comes out of the system. Exothermic, heat comes out of the system. Endothermic, heat goes into the system. Now, if we want to actually study the heat transfer in a lab setting, we do a process called calorimetry. And we do calorimetry in a container called a calorimeter. And a calorimeter just has to be an insulating container to keep all the heat in. A very easy calorimeter is a styrofoam cup, and that's what we're going to be using in class. Styrofoam is a really good insulator, so whatever's going on inside the cup, that heat transfer is going to stay contained. It's not going to go into the container. So when we use our styrofoam cup calorimeter, we will also need to use a thermometer to measure the temperature change that's happening as a result of the heat being transferred into or out of the system. Okay, so let's look at an example. All right, let's say with our example that we have a hot object and it's placed in room temperature water in our styrofoam cup calorimeter. We want to describe the heat transfer. So if our object is hot, it's at a higher temperature than the water, what's going to happen? Well, the hot object is going to transfer heat to the water until they get to what's called thermal equilibrium. And thermal equilibrium basically means that two things are at the same temperature. So if you have a hot object and you place it into contact with a cold object, the hot object is going to give the cold object heat until the two objects that are touching are in thermal equilibrium, until they reach the same temperature. So you can see here, if we put something into the water, let's say a piece of metal, and the metal is hot, like we described in our example, then it's going to give heat to the water, which is considered the surroundings, right? You can see the temperature of the water increases until the metal and the water are at the same temperature. So the heat that is lost by the metal is equal to the heat that's gained by the water. The heat that the system loses is equal to the heat that the surroundings absorbs. So you can see that example of calorimetry, and we're going to be doing some of this practice in class in a lab, actually measuring all of the stuff that goes into this heat transfer. Now, when we do this lab, we can't actually measure heat directly. We can only measure the temperature change due to the heat transfer. So, like we saw in the demo, the heat transfer is related to not only the mass of the substances involved, but also what they're made out of. We saw that the different metals transfer different amounts of heat to the water. So we have to know several variables in order to calculate the heat that's involved in these heat transfers. And the formula that we're going to use is Q equals Cm delta T. Q, that's our heat transfer. And if you remember, we talked earlier that our units are joules, capital J joules for heat. And the specific heat, that is a property of the substance. That's basically how much heat it takes to raise the temperature of 1 gram of that substance 1 degree Celsius. So the specific heat is either going to be given to you because it's a constant for whatever your substance is, or it might be something that you're solving for. But the units of specific heat are joules per gram degree Celsius. So it's how many joules does it take to raise 1 gram of the substance 1 degree Celsius. For the M is going to represent mass of a substance, and we'll measure the mass in grams. And then the delta T, anytime you see that triangle, that means delta. Delta represents change in. So delta T, change in temperature, and we're looking at the initial temperature and the final temperature. And to calculate delta T, we're going to take the final temperature minus the initial temperature. And that's going to be in degrees Celsius. So we take the final temperature minus the initial temperature. Now, that could be a negative number if your temperature goes down, which is fine. That just means that you're going to get a negative value for Q, which is perfectly acceptable. It just the negative or positive Q just tells us if heat is going into or coming out of a system. So we're going to be using this formula when we do our labs. You can calculate any of these variables as long as you know the other three, but for now we need to look at Q in joules, specific heat, which is joules per gram degree Celsius, mass is in grams, temperature change will be in degrees Celsius. So make sure you know that formula, make sure you know what units all the variables are, and come to class with your calculator prepared to do this exact calculation.